Okay. YouTube is going as well. We're healthy. Cool. Doesn't look like anyone's. Okay, we got maybe one person watching me at the moment. Fine. Okay, so streams are healthy. Let's make sure that's coming through. As I like. Yeah, the hello YouTube chat doesn't really seem to come through at the moment. Might be a little slow. Keep an eye on it. Okay, so welcome to the second stream where we're going to be looking at the Frost Kitten 33 Virtex HBM FPGA that has, like in the picture you see here, two large memories on die. We're going to throw down the MicroBlaze so we can do some like very simple memory addressing and do some reads and writes to the memory and kind of verify that the hardware is working as we expect. A quick thing that you feel free to follow me on Discord, YouTube, Twitch, or Twitter X. I think the Discord and the GitHub link should be in the description. I might add the other ones later. So let's go and look at the new design. So last week, or last stream, we were having issues with the Smart Connect not properly decoding the address. I was using a pre-built example design. I didn't really like it, so I kind of trashed it, and we started a new design. So let's go look at that new design real quick. So there's a condensed view, interface view. Okay, this is probably easy to understand. Color coded. That's an ugly color. Addressing view. We'll just do interface. Okay, so this is what we've done. It's a very, very simple design. We have the MicroBlaze. We put this one up to be performance, but we kept it 32 bits. We added the cache. We added caches, and that's about it for here. We have the local memory that we're going to run our MicroBlaze code out of. Then we have, we're not actually using LEDs, but we do have the Smart Connect connected back to the MicroBlaze debug module, and this is acting as a UART, or a serial message port that we can access during our software. And then we have the HBM. So I did kind of a unique configuration on the HBM, so let's walk through that real quick. With the MicroBlaze, the start address is always at the beginning. So I decided to skip the memory modules on the first half. I decided to skip the first 2 gigabytes of memory in the module. So we're going to just we're doing the left stack. We're not doing both, we're just doing the left stack. And we're just going to activate the second 2 gigabytes of this 4 gigabytes. And I just picked a single axis because it's like a 4:2 ratio in these interfaces. So I'm just going to do one axis port for 2 of the MCs. And we're just running it at the normal 900. But yeah, the input clock 200. We have some debug module on, which I had to do some fun constraints to get that working. I'll show that to you in a sec. Okay, so next, the important thing. Really. Okay, this is what I wanted to see. Why is this in the browser? It shouldn't be in the browser. That's weird. Browser? Why is it not local? Okay, so this is how we've done the addressing. So the MicroBlaze, we have 5 different buses. This is kind of nice, so you can see which bus is going where. That should be on. Oh, yeah, these are excluded. That interface. Yeah, this. I have to click these to get the ones I want. Yeah, I don't like that view. Yeah, that view doesn't really work the way I've structured it. So if we actually look at this, what we've done is then the first four memories, it's in order. First four memories are on one AXI port. The last four memories on the other AXI port. But we should get optimal reads and writes. I mean, we're not going to be reading or writing that fast, but we should get optimal reads and writes for this interface. And we do the same thing for the instruction bus. Okay, so I wanted to add, I'm going to mark these as debug. I wanted to snoop them on a new screen. Do that one first. Both of them. Okay. Let's make sure this is configured correctly. Okay, so hopefully this goes to the correct debug port. Yeah, we just need data and capture, data and capture. We want to increase to, that should be fine. Okay. Validate this. Show you the print file, get this building, and then we're going to go through the Vitis project and show you how the Vitis project is built for this design. So, going to the constraints, I found this on a Xilinx forum, and basically there's an issue for the block diagram to find the correct clock for the HBM debug module. So this is basically stating that the debug module that's that HBM is using is going to use the first B scan, and the clock is this specific net. For some reason, the tools lose that. Save this, right? We're going to rebuild this, and why this is building. Let's go ahead and pop open the Vitis IDE. Great, how long tools take? Okay, Vitis is right here. We're going to change it to a new SDK because we're going to do this from scratch. While we're doing it from scratch, we're going to build a new design in the background with these new ILA cores. There are right here, ILA cores. They're snooping the AXI 3 buses. Be fun. Okay, so we're all good here. We should be able to close the input line and go ahead and generate a bit string. Okay. So we're going to go ahead and create an application project. So we export an XSA file. I can show you later how we do this, but XSA file is pretty easy to export. So we're going to grab the XSA file that describes the MicroBlaze and the interfaces it's connected to. This one doesn't have the bitstream. It can have the bitstream, but this one doesn't. So we're going to go look at a MicroBlaze memory test. Let's go ahead and bring up the sickle shell so we can program against our oh, supposed to be doing this at 1080p. Must be hard to see. Give me a second. Okay. Why does this already fail? Messages to do. Okay, let me fix that real quick. Okay, we're good. Generate this. Okay. We have that in the background. Next. Okay. 3. Okay, cool. B. Looks like it's powered. Okay. Pretty good. Okay. Detect targets. Okay, it looks like it's appropriately actually that's lacking the MicroBlaze. So we're going to go FPJ help and no revision text. F F 1.5 oh vision. Okay, cool. Add that to my to-do list next time. Yeah. Okay, hopefully everyone can see better now. I didn't get any complaints last time from no one being able to see. Okay. So we programmed the bitstream. Now we're going to build the memory test. So let's first look at the project here. So in the board support package, we have our LEDs, our UART, our memory, and some local memory here. They don't really have, the HBM doesn't have any specific information. I guess it's just memory space. So we have the MDM for standard in, standard out. Is there anything else? Do they have anything for the HBM? It just says generic. Take it. Okay. So let's go ahead and just build the generic one. And we can run it on the design. Really need to edit this chat box so it doesn't, it clears up. That delay. Figure out that hello Twitch. If anyone has any questions, feel free to ask. It doesn't look like we have a lot of viewers at the moment. Feel free to ask questions now and later in any comments section or whatnot. Okay, so the bitstream is done. We're going to click on debug. So click on the mem here. We're going to say run launch hardware. This will run it onto the MicroBlaze design. Here it went through each memory range, right? So we divided them into 256 megabyte chunks, and it's going through and just reading each of them. Can we hardware manager while this is running? See if we can look at the status. Dashboard, new dashboard. Let's add both of them. Doesn't look like. I guess we'll add this one. Okay, let's try running the program again. See this throughput changes. Nothing to notice. We pause it. Log. Must not be actually that demanding. We do have changes here when we ran it. Okay. Rerun it. Okay, we have samples. Now let's go back over to here to the code. Stop and start it. So if we go to the memory test platform, basically what's happening here is we're going through each memory range, and we're running this simple application. So it's going to print out the base address, size. It's going to be doing 4K by reads and writes as different sizes. So let's go ahead and increase these by 1K and see this. This is where the memories are. We can see each independent memory region. Okay, so we're going to rebuild, rerun it, and see if it actually changes. I want to get this debug module to actually see something. We actually, are we seeing anything? So that's where we saw it. And that was 2.5. That was pretty good. So we're going to stop. Let's make this. Let's, I guess, minimize this one. We're going to pop out this. And let's add activity monitors for everything. Selected average. The code is still running, so I guess we'll just play it and see where it goes. Okay, we successfully stop it, rerun it, run this processor test again. Okay, so it's like not showing all of them. Okay, that's where that one spikes. Samples seem like weird locations. The sample rate is garbage. Okay, but this is interesting. We can see the different channels that we've selected. Magenta, we get the gray, blue. Okay, test finished. So go ahead and pause, look at the activity log. Yeah, okay, I think we just need to run them longer. So let's go ahead. Use it. Let's be a lot longer. Maybe we could, but we can't. I want to do it in parallel, but it's not really easy to do in parallel at the moment. Okay, let's go ahead and rebuild it. Stop this. And start run. I wonder what the temperature is going to get different. Yeah, we got 3.5. That one's always kind of a interesting spike. Yeah, this activity monitor is just weird. Like some are constant, some are spiking. Temperature's still solid. Good. Okay, that's interesting. So when we went to the 8-bit reads and writes, our performance spiked to 5 gigabits per second. Then we dropped down. Might be a little too long. The how is the Lovato project in the background? We're still place. I mean, we got time. So who wants to watch HBM performance charts? Hmm. Okay. How are we doing? Are we gonna finish the other one? Okay. We move on to the next memory. This one's spiking as well. Temperature is solid, but we got pretty good, right? 1 gigabits per second. We're just doing one channel too. We're not even like spamming this thing. Sample rate is okay. Let's just get to the red and yellow ones, which were slightly different because there was the red and yellow ones are technically on like a different switch component. I wonder that's what's changing this up. So orange and blue behave the same. Red and yellow should behave differently because the switch has to kind of do some minor changes. But according to documentation, that shouldn't affect the performance. But I feel like we'll have a different. Will look differently because the switch is pipelining the reads and the writes. Maybe because it's pipelining it. That's able. Okay, here we go. So the red one, this one. So in the red one, the switch has to change it a little bit to access the other memory. They're definitely getting more consistent. Okay, this would be fun to put some traffic generators on and play around with how the XE and the memories interact with each other. Or so what's the overall the temperature on the other part of the part? PJ is only at 26. Okay. Okay. How is the rest of the FPGA doing? Still running place design. Hoping that would finish a little bit. Transformation log. Okay, we just finished place. We're going to route. That's good. Yeah, go back to hardware manager. Okay, so what's our maxing at? Our maxing 6.4. That must be the switch. Okay, interesting. Okay, it's gonna take probably a few minutes for the other design to finish. Let's see. Is there anything interesting? Well, we could try to do um try to do any men tests in parallel. We could try to spam the right of the MicroBlaze and see what comes up. But it is a cache. Oh, maybe it's a cache. That's the cache dump and the cache. Do we disable the cache in the platform? Okay, so when you do the platform.c, right? We have like enable, disable caches, and we enable caches. Let's see what we do here. We have an init platform. That's what cache disabled. Where do you disable it? Big. Oh, let's see. Init. Whoa. Okay, we have a function. I don't think you actually disabled the cache. I think you lie. You can step through it. There's Did that. Okay, may not be happy with me. The blue one's a lot steadier. Yeah, let's see what happens when we disable the cache. Okay, run it. Okay, go ahead and build. Go ahead and run it. And now it's still spiking. Okay. It didn't help. Okay, I don't think we can effectively use the debug or the MicroBlaze DMA core. Okay. We're writing the bit stream. Then we can go look at the messages. I was just going to hunt down into the MicroBlaze. MicroBlaze has like an axis stream built into it. Okay, a bunch of low-level commands. Some of these access. DMA. Okay, I think we're good. Yeah, okay, cool. Close this. The bit stream is down here, so let's go ahead and get the other bit stream working. We are going to export this bitstream file. Open up the hardware manager here. Go reprogram that with the other one. Then we can get the ILA cores working. Fresh devices, hardware ILA. Here's the we need a load to be able to where's the probe file? Probes. Here we go. Why is it so? Oh. Okay, cool. Okay, now it's happy. I had to trick it so that when you went to probes, it has a correct file now. Okay, cool. Get rid of that. Get rid of that. Get rid of that. Okay, so we have these AXI3 interfaces. We're going to trigger this out. And we're going to create a trigger based upon both of them. And what's the good? That is the best one to stick it on. Do W valid? Yeah, let's do W valid for both of them. So W valid, and we're going to want to say 1. Add another trigger for W valid here. 1. Okay, now we can run. Actually, stop settings. Want the depth there. I want the trigger position to be 32. Okay, cool. That's good. Let's go back here to this test. Would be good. 128. Oh, no, bad. Control S will be, and okay, now we're gonna run it. Okay, stop. Give me active, inactive. Okay, apparently those were not us using the other channel. Okay, AW. Okay, so let's run it again. Then this. So a lot of reads. I think the right side. So, the read the R channel are valid. Not right channel. I feel like, I don't know, let's go back. I want to open declaration. Yeah. Yeah, so they're writing the values, then reading the values. So we just gotta be in a read section. Wish there's a way to be like trigger on the transaction. We do have AW valid. Grab that. And grab. Okay, try this one. Run. Okay, go. Oh, sorry. I know why it's not. My bad. We want these as a global OR. Then we want to run it. Okay, we might have been right at one. network. It was it does go high. It's just that we had the global and instead of the global or. Okay. Okay, so let's drop title from that one, figure off that one, and run. Okay. So now when we get to A, yeah, so we grabbed it. It's going to take a moment to say, okay, here we go. And it was with this C address. Okay, I'm curious about the, so F E E C. Okay, yeah, so it's the C that it's the first one. And I want to zoom in. Oh no. So how wide are these transactions? Okay, we're not, doesn't look like we're bursting in. It looks like we're writing it word by word. Okay. Okay, so I think that's about kind of all we're going to show today. But yeah, to recap, we've looked at the um, we've looked at the HBM debug core. We snooped on the Axie 3 interfaces as well to see how their transactions is going. And we're able to get the MicroBlaze to simulate those different address ranges. So next goal is we want to use traffic generators. So let's look at it real quick. There's two different types of traffic generators we can look at. So um, we open up the HBM core. They have internal to the HBM traffic generators. I'm not sure if these are soft or somehow in the hardened controller. Um, Probably go read about these. Oh, this is just control. So that's just, it doesn't actually do traffic generation. It controls the traffic. Um, or random. That'd be interesting to try out different things. Okay, so go that. What we want to do is we want to add IP. We're going to go traffic. We can Axie traffic generator. We're going to go default view. And let's go check out what the traffic generator is. Let's see, what's high level traffic? That's actually doing real data custom. Static. Advanced. Okay. I'm going to read about these data width. Yeah, we want to get that as big as possible. Um, 32. Well, we want to do 64 so we can deal with these. And we're going to have to find. Okay. Let's see. Can I open up the documentation? What's gonna open up when I click that? Okay, so I'll probably have to read up. I'm gonna go do my homework. I'm gonna read about the traffic generator. We're gonna hook up 16, no, 32 of these. We're gonna hook up 32 of these to the DDR, and we're gonna have them working only on a specified memory range, and we'll see how the system reacts to that when we just spam write ports. Not the read ports, writes. I think there's IP. What is it? Traffic. I think there's some way to verify your traffic. Okay. So that's probably where we're going to end here. We're going to get this traffic generator up and going, 32 of them, to the HBM and be able to monitor how they work. Join us, I would say, later this week. I don't have a good schedule at the moment, but we'll figure it out. Thanks for joining me. Feel free to subscribe, follow, yada, yada, yada. Hopefully we can dig more down into this traffic HBM. Hopefully we can start looking at PCIe bandwidth testing and hopefully Vitis AI. I think Vitis AI would be interesting here, but I'm gonna have to set up a Ubuntu environment to do it. Okay, I'm gonna think about that. Where can I set up the Vitis AI environment? Oh, it's gonna be pain. Vitis AI being Linux only is useful for some things, annoying for other things. Okay, good night.